Hey everybody, it's Miss Berry. In this video today, we're going to go over section 4.4, which is called the inverses of functions. So today we are going to be beginning with the idea of something more general, which is to find the inverse of a relation, which is a lot easier than finding the inverse of a function. So it says, consider the following relation. It says step one is we have this set of ordered pairs T. T is equal to the ordered pair negative 8, 3, negative 9, 9, negative 6, 2, and 7, negative 8. It says find the inverse of T and express your answer as a set of ordered pairs. So whenever we write the inverse of a relation or of a function, we use special notation. So instead of writing out like inverse of T, which would take us a really long time, we have some shorthand notation that we can use, which looks like this. So you just write the name of the function or the name of the relation. In this case, it's T, and then you write it with a -1 in the exponent. We'll talk more about that in just a minute, but just know that that is the notation that we use for the inverse. All right, so it's going to be a set of ordered pairs, and super easy to find the inverse of a relation. You just switch the first and second coordinates of each of the ordered pairs. So you're just going to switch these, switch the first and second coordinates. So this is going to be 3, negative 8. The next one, again, we're switching. So that would be 9, negative 9. The next one would be 2, negative 6. And then negative 8, 7. Super easy. Okay, so when you're finding the inverse of a relation, again, you just switch the first and second coordinates of each of the ordered pairs. Step 2 wants us to find the domain and range of our inverse. It says express your answer as a set of numbers. All right, so we're going to be finding the domain of the inverse. So the domain of T inverse and the range of T inverse. All right, so recall that the domain is the set of the first coordinates. All right, so the domain, again, is the set of the first coordinates. So that's going to be 3, 9, 2, negative 8. All right. So, and again, it's a set. Domain and range is a set. All right, so we have the domain of our inverse relation is 3, 9, 2, and negative 8. They are not written in order from smallest to biggest, and that's fine. They don't have to be. All right, so you do not have to put it in order from smallest to biggest. The range, recall, is just the set of the second coordinates. That's going to be negative 8, negative 9, negative 6, and 7. So again, set notation, curly braces, negative 8, negative 9, negative 6, and positive 7. There's your domain and range. So finding the inverse of a relation in the domain and range of that inverse is super easy. But let's talk about specifically what this section is about, which is about finding the inverse of a function. So just to remind you, we use the following notation to represent the inverse of a function f. So it's f and then a -1 in the exponent. And then your book has this little word of caution. It says we're faced with another example of a reuse of notation. Note that f to the -1 power, that does not stand for 1 over f when f is a function. This is really just representing f inverse. Again, this is read as f inverse. We use the exponent of -1 to indicate the reciprocal of an algebraic expression or number, but when it's applied to a function or a relation, that just represents the inverse relation or the inverse function. All right, so that is the notation that we'll be using to represent the inverse of a function or the inverse of a relation. But let's talk about how we actually find the inverse of a function. We have a really nice test to help us determine if the function has an inverse. It's called the horizontal line test. You may this may sound familiar because we had the vertical line test earlier in the semester. Remember, the vertical line test tells you if the graph is a function. The horizontal line test tells you, let's see, we'll say this tells you, actually, we'll just write out the actual test. If a horizontal line passes through the graph more than once, then that function does not have an inverse. Or actually, let's say, how do I want to say this? Sorry, you guys. Then that function goodness gracious. Sorry, I just want to erase this last part and rephrase it so that it makes sense. If the horizontal line passes through the graph more than once, then that function is not one-to-one. So that function is not what we call one-to-one. So, for example, say that we have a graph and it looks like this. All right, so imagine if we just drew a horizontal line through here. If we drew a horizontal line through here, notice that it passes through more than once. So that means that this function in green here is not one-to-one. So let's talk about what does it mean to be one-to-one. You can see in the little green box down here, I've got the definition of one-to-one. It's kind of complicated, but I'll sum it up at the end. It says, a function is called one-to-one if for every pair of distinct elements x1 and x2 in the domain of f, we have f of x1 does not equal f of x2. That means that every element of the range is paired with exactly one element in the domain. Now that should sound kind of familiar because that's very similar to the definition of a function. It's just the opposite. So it says, this is really the important part of this definition here that I'm highlighting. It says, every element of the range is paired with exactly one element in the domain. So that means that if you plug in a number, say we plug in 1. And that equals 2. We should not be able to plug in another number and get 2 again. And that's what's happening here. So you can imagine if you plugged in, let's say 1, and it was right here. All right, if you plug in, maybe this is, we'll just imagine that it's 2. So it's the y value 2. But notice that if we plug in this number over here, maybe it's -1, I don't know. We just made up this graph. Notice that it's going to give you that exact same y value. So we don't want to get the same y value for 2 x values. So hopefully that makes sense what that definition means. All right, so we do not want to get the same y value by plugging in 2 different x values. Now, to sum this up, the inverse f inverse of a function f is also a function if and only if f is 1 to 1. So that means, for the purposes of our class, if the graph passes the horizontal line test, HLT, then that function is 1 to 1, which means it has an inverse. Function. All right, so if the graph passes the horizontal line test, then that function is 1 to 1, which means that that function has an inverse function. All right, so if the graph passes the horizontal line test, that function is 1 to 1, which means it has an inverse function. All right, so let's look at a couple of examples where we just determine whether or not this function has an inverse function. We'll come back to this in just a second. I'll come back and talk about why I have this here. All right, so number 2, we have a part A and a part B. All right, so it says determine if the following function has an inverse function. It says h of x equals the square root of x plus 1. Now, you could take your graphing calculator and graph this and look at it that way. But an easier way to do that would be to kind of think back to what we did in section 4.1 and say, like, what is the basic function that this comes from? So you kind of refer back to your page that I gave you of basic functions. And which one does this look most similar to? Definitely looks most similar to the square root of x, which is right here. So we're just going to look at that graph and we're going to determine, does this graph pass the horizontal line test? So could we draw a horizontal line and have it pass through more than once? So is there anywhere where we could move this horizontal line and see that it passes through the graph more than once? No, there's nowhere where this graph, or excuse me, where this line is going to pass through the graph more than once. So that means that the function passes the horizontal line test. So we'll go back here and we'll say y equals square root of x passes the horizontal line test, which means that h of x does have an inverse function. So h of x does have an inverse function. All right, now let's look at the second one. S of x equals x squared minus 3x. What is the more basic function that this one comes from? That would be just x squared. So let's go and look at the graph of x squared. All right. Here is the graph of x squared. It's right here, this quadratic. And notice that anywhere where we place this line, unless it's down here, of course, but if we place this line on the graph, it's going to pass through more than once. That means it fails the horizontal line test. So we'll say y equals x squared fails the horizontal line test. So therefore, S of x does not have an inverse function. So if it passes the horizontal line test, it has an inverse function. If it fails the horizontal line test, it does not have an inverse function. All right, so let's talk about how we find the inverse. Now that we know how to determine if a function does or does not have an inverse, we're going to figure out, okay, so if we determine that it does have an inverse function, how do we determine what the inverse is? So finding the inverse of a function. There are 4 steps to finding the inverse of a function. Step 1 says replace y with f of x. Whoops, I said that backwards. I'm so sorry, you guys. I can't get it together today. Replace f of x with y is what I meant to write. Sorry. Replace f of x with y. Okay, so that's step 1, replace f of x with y. Step 2, switch or interchange x and y. So you're just going to switch x and y. Step 3 is solve for y. Step 4 is just replace y with the inverse function notation, f inverse of x. Good night in heaven. Replace y with f inverse of x. Let's see if I can do this without having to rewrite everything. Oh yeah, there we go. Replace y with f inverse of x. All right, super easy steps. This whole process is pretty simple. The step that takes the longest is step 3 when you're solving for y. Sometimes this can be complicated, sometimes it's easy. It just depends on the function that you're working with. But let's look at a couple of examples. This will be number 3. It says, find a formula for the inverse of the following function if possible. All right, so we have to determine, first of all, does this have an inverse? So we have a of x equals the cube root of 3x plus 4. So this comes from the more basic function or the basic graph, the cube root of x. So let's go back and look at the cube root function. So here's the cube root function. Let's grab our little horizontal line. All right, so anywhere we put this horizontal line, it's only going to pass through once. All right, so anywhere we place that horizontal line, it's only going to pass through one time. So that means this function passes the horizontal line test. Which means a of x has an inverse function. Okay, so now that we know an inverse exists, we can go ahead and find the inverse. All right, so we have step 1. Remember, we're supposed to replace the function notation with y. So we're just replacing a of x with y. So we have y equals the cube root of 3x plus 4. That was step 1. Step 2 is to interchange x and y, or switch x and y. All right, so that y is going to become an x, and x is going to become y. All right, step 3, which again is the step that takes the longest. Step 3 is to solve for y. So we're trying to get y by itself here. The first thing that's standing in our way here is this cube root. But we can cube both sides to get rid of that. So raise both sides to the 3rd power. All right, so raising both sides to the 3rd power. On the right-hand side, it's going to cancel out. And we have x cubed equals 3y plus 4. All right, again, we're trying to get y by itself here, so subtract 4. trying to get y by itself, divide by 3. Divide the whole thing by 3. You can divide each piece individually by 3. It does not matter. But you get y equals x cubed minus 4 all over 3. Now, we're typically used to seeing y on the left-hand side, so if you want to switch that over, that's fine. All right, and then our last step, step 4, is to replace y with our function notation. This function was named a, so we're going to call it a inverse of x equals. So y just gets replaced with a inverse. Everything else stays the same. And that's it. That's your inverse function. Okay. We have one more. So let's do this again. This will be number 4. It says find a formula for the inverse of the following function if possible. This one is also named a. So again, step 1 is to replace a of x with y or f of x, whatever your function notation is. Then you are going to interchange x and y. All right, now we're solving for y. Okay, so let's go ahead and get rid of this fraction by multiplying both sides by the denominator. So multiply both sides by the denominator. It's going to cancel it out on the right. All right, so on the right-hand side, this cancels. All right, and we're left with, let's do 3y plus 2, sorry, I'm getting a little sideways here, times x equals -5. All right, we're going to multiply 3 by x. So that's 3xy plus 2x equals -5. All right, so again, remember our whole goal here, we're trying to get y by itself. So let's work on getting y by itself. So subtract the 2x. So that's going to equal -5 minus 2x. Cancels out on the left. So that's 3xy equals -5 minus 2x. Trying to get y by itself, so just divide by the other stuff. So divide by 3x. And you have, on the left, it's canceling out. 3x and 3x cancels. You're just left with y equals -5 minus 2x over 3x. And then our last step is to replace y with the inverse function notation. So that's, in this case, going to be a inverse, because this one was named a. A inverse of x equals -5 minus 2x over 3x. And you're done. Okay, let me move this up a little bit so it's not cutting anything off there. All right, so that is a short video on how to find the inverse of a relation or the inverse of a function. Please let me know if you have any questions. Otherwise, I'll see you guys soon.